Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the blind Leetcode 75 problem list. Today I will be doing problem 572, which is called subtree of another tree. So let's get to read the problem statement. Given the roots of two binary trees, root and subroot, return true if there is a subtree of root with the same structure and node values of subroot, and false otherwise. A subtree of a binary tree is a tree that consists of a node and tree and all of this node's descendants. The tree could also be considered as a subtree of itself. So if we have this root right here, it contains the subroot because we have the exact same tree inside here. And here in example 2, it does not contain it because even though this tree right here is the same as this, the 2 has a child, which is the 0 here. So yeah, that's why this one returns false. So if you want to try this problem by yourself, now will be the time to pause the video because I'm going to explain the approach. All right, so first of all, right, what we can observe is that we have to find the exact same tree within the tree, right? Meaning that at any point, right, if the current tree is equal to this tree, then the function will for sure return true. In this case, if we are in this node, right, and the subtree where the root is this node is equal to this tree right here, then what we're going to do is we're going to return true. But what if the subtree starting at the current node is not the same tree as this? Well, then all that we need to check is whether the left subtree contains the subroot or the right subtree contains it. And that's pretty much the entire idea behind this. And in fact, we're going to be recycling code from one of the previous questions that I've solved already on the channel, which is the same tree question. So let's get to it right here. I actually have it opened. So let's just get to copy this. We might have to modify some keywords like self and all that. But the main idea here, right, is that we start at 3. And what we need to first check, right, is whether the first thing that we need to check is whether like if we are currently at a root, right, at a place where the current root is none, then that means that the algorithm will just not work. Because, if the root is none and the subroot is not none, then, well, that's pretty much it, right? There's no more to check there. But the main idea is just, okay, we are at this root right here, root 3, and all that we're going to check is whether the tree starting at this node is the same tree as this. If it's not, then we're going to check the left subtree and the right subtree. And if any of those return true, then obviously the function will return true. Else, it will return false. And when I say the same function, I mean that we're going to pass the is subtree function, important thing here, not the other one, the same tree function. So let me just indent this. Okay, and then I have to get rid of the selves. Okay. And in fact, I think I might be able to optimize this a little bit. I see that some of the cases here. Okay. So I guess I can optimize the is same tree method a little bit. This right here, I think it's good. And then in here, I think the only thing that I really need to do is just, let's see. So if p is equal to none and q is not equal to none, or p is not equal to none and q equals none, then we return false. But I guess what I can just check is this, right? If p is equal to none, or q is equal to none, then we can return false. And the reason why I can do this, right, is because the only case in which either p or q is going to be none is whenever one of them is not none, because we've already checked that that case right here, right? This would be the case where, suppose that we have a truth table, right? We have P can either be false, false, true, true, and Q can be false, true, false, true. So we've already, suppose that this, like, false, let's see, so is none. This is a value table for is none. So both of them are true, so both of them are false. That's covered by this, right? So then the other cases will be either this one or this one. So whenever we reach this point in the code, then we already know that P and Q are something. So they are not none. So that's why I can just write this. And then after that, I think all that I need to do, right, is just return whether this is true. And yeah, that's pretty much it. I think that'll be a slightly faster check. In fact, I think what I'm going to do is the following. I mean, since you guys have already probably checked that video before, I'm going to put that here so that the logic can short circuit, because a lot of times this might be even faster. So, and this is equal to true. Okay. So if this is the case, then it's true, else we return false. So that'll be the same tree. And now, like I mentioned before, right, we have to check the is subtree. So what do we do with the is subtree? Well, the first thing, right, is that we need to use some sort of helper that can help us traverse the tree, right? And simply what we're going to use with that is, you know, that we're going to pass the same elements, so the root and the subroot. So I'm going to say define helper root subroot. And the main idea, right, is that at any point we're always going to be passing the same subtree, so subroot. We're always going to be passing the same thing. So this, no matter what, will always be the same thing. And now what we need to check is, the first thing is if the head is equal to none, right? Because as it says here, let's see, the number of nodes in root is at least, and subroots is at least 1. So since the subroot will never be none because there will always be at least 1 node, we know that whenever the root is equal to none, then that element, right, that tree will never be equal to the subroot. So if sorry, not head. So if the root is equal to none, then we return false. Now, the second thing that we need to check is whether the tree starting at the current root, so here we would start at 3, right? So if is same tree, and we have root and subroot, so if that's the case, then we return true. And the other case would be, well, they are not the same tree, but it could be that the tree is contained within the left or the right child, like it happens here, right? Here, for example, when we start the method and we call is same tree here, so the helper, so if we call it in 3, it's obviously going to return false because 3 is not the same as 4. But if we explore the left child and we go here, then we see that this right here is equal to this tree right here. So not only we need to check the current tree, but we also need to traverse the left and the right subtrees. So, and what we're going to do next is, if this is true, so if that's not true, sorry, then what we need to check is whether whether the left child contains the subroot, or whether the right contains the subroot. And I think this should go here. There you go. And I am not sure if I need to declare this maybe below this, since is same tree is not defined yet. So I'm just going to do that here real quick, just in case. There you go. And after that, all that we need to do is return helper root subroot. And this should work. A little bit slow. Eventually, it beats like 60 or 70% of the solutions like I've tried it here. But yes, so now we can discuss another way to solve this algorithm, but this is probably something that you would not be asked in an interview. Well, I guess internet is a little bit slow today, but eventually it beats like 60-70% of the solutions because I tested it before. So another thing that you can do, right? And I would say this is a bit hacky, and that's why I wanted to show you guys this solution right here, because this involves, manipulating trees and all that stuff a little bit more and using recursion, which is more or less what the interviewer would look for if they ask you this question. What you can also do is you can process the tree, right, in some sort of like in a pre-order traversal, let's just say, right? And what you can also do is, at some point, if you perform the traversal, you can transform that into a string. So you have a string that represents the traversal of this tree. And then you perform traversal of this tree and return a string. So you have two strings that represent the same. It's important that they are the same type of traversals. And what you can check is whether this string right here is contained within this string. And the reason why that will be more efficient is because there are some algorithms, like the KMP algorithm, for example, that can find a substring within a string in linear time. So, the runtime of that algorithm will be O of n plus m, where n is the length of one string and m is the length of another string. And now let's evaluate the runtime, right, of our solution. So in the worst case scenario, right, for the solution that we implemented, so suppose that the root looks like this, okay? Some simple example. So you just imagine that you have like a bunch of ones, right, like that. And eventually, you go like 1,000 levels deep, let's say that. It's always just going to, I guess, well, I mean, it doesn't say that they're binary search trees, they're just binary trees, so that's fine. Great. And then you have another subtree. So this would be the root, and the subroot is exactly the same thing, right? But at the end, you have this right here, the 2, right? So imagine if we're doing this, right, all the time, when we start on the root and we start comparing with this right here, we're gonna go as deep as we can with this, right, until the last element. Suppose that there are more elements in here, at least as many elements in here as there are in here. Okay, so suppose that there's like I don't know, like 1,000 ones. And here we have 999 ones and 1, 2 all the way at the end. Okay. So what happens here, right? Like our algorithm, what it does is it first checks whether the current thing, like it says in here, let's see, helper. So it checks whether the current tree is the same tree. So if the current tree is the same tree, right? Then first what it does, it just checks everything all the way down. So it goes 1,000 levels deep. For the next element, right? We go, so this is a subroot, so now we go to the right child because there's no left child. And we perform the same thing, and now it goes 999 levels deep because this only has 999 levels. And so on, right? So what you can see here is that we are performing this recursion, like we're going deep in the subtree over and over again. And what you end up seeing, right, is that we traverse this entire thing, or this, whatever is smallest, but we do this over and over. So the runtime complexity of this algorithm is big O of m times n, where m is the number of nodes in one tree and n is the number of nodes in the other tree. And the spacetime complexity will be big O of n, where n is the number of nodes. So it's I guess the spacetime complexity, sorry, is big O of the maximum height between the two trees, because that's as deep as the recursion is going to go. It goes as deep as like the height of the highest tree, or the depth of the deepest tree. I don't really know how to call it, but yes. So that'll be it for this video. I hope you enjoyed it, and yeah, make sure that you leave a like, which helps the channel a lot, and see you in the next one. Bye bye.